Okay, so for an ideal solution, we have an expression for how the vapor pressure of a specific component above the solution varies as a function of the mole fraction. Right, it's just the simple equation Pj equals xj Pj star. For non-ideal solutions, you can write out expressions that are sort of like this, but they have more complicated functional forms. We won't really look at them much. We'll more look at when we would expect deviations, but not necessarily quantitatively how we would account for that. Anyway, we will quantitatively look at Raoult's law, though, and ideal solutions to give us sort of a baseline expectation. So we can use this, we can plug this into our equation for chemical potential for our solution. So that's going to be equal to mu j star of our liquid plus RT natural log of, and now we can plug in Raoult's law for Pj on the top here, so it's xj Pj star divided by Pj star. Those cancel, and so we get that the chemical potential simply depends on the log of the mole fraction. So we get this plus RT log xj. All right, and this is that same version of the chemical potential we looked at with the Gibbs-Duhem equation. So we can say that if one component or one phase follows this, the other one follows it as well, right? And this will hold for both components. That's what we showed with the Gibbs-Duhem equation. So now let's look at some properties of our system. So what's the total vapor pressure, right? Well, that's going to be the vapor pressure of our two different components. But now we can write those out according to Raoult's law. x1 p1 star plus x2 p2 star. So to actually find this, we need to know the composition of our solution, as well as what the vapor pressures of the pure substances are. We can rewrite this as, write it in terms of just x2 here. So 1 minus x2 is the same thing as x1 times p1 star plus x2 p2 star. And we can then simplify this to p1 star plus x2 times the difference in p2 star and p1 star. Okay, if we look at p total as a function of composition, just according to this equation here, we get a pretty straightforward looking plot. I'm just copying and pasting it here. All right, so this is a figure from your textbook showing how the vapor pressure of each component changes. So basically looking at this equation here, and we can see we get straight lines, right? So we have, this is an example of benzene and toluene. Like I said, this is something that forms a pretty ideal solution. Our total vapor pressure will just increase as we increase the amount of benzene. Benzene has a higher vapor pressure, so our x-axis here, getting used to looking at these sort of plots, is the mole fraction of benzene. So this point over here on the far right, this is the vapor pressure of pure benzene. And so that's if we have pure benzene on the left, and then over here is the vapor pressure of pure toluene on the left, and on the right is pure benzene. And so benzene is more volatile than toluene, so as we have more benzene in the solution, the overall vapor pressure will increase. And as we have less benzene in the solution and it's more toluene, the vapor pressure will decrease overall for the solution. And we can see each of benzene and toluene, they have this straight line behavior. This is following Raoult's law, right? So this is just this behavior here. And then when we add them together, we get an overall linear trend as well. Okay, so, but one important thing to think about is that if you have, this, right, if we're sort of picturing, we have our mixture of benzene plus toluene in equilibrium with the benzene and toluene vapor that's above it. One important question to think about is, say we know the mole fraction, right? Say that we have that the mole fraction of benzene in the solution is equal to 0.5. So we have exactly half and half in terms of number of moles, benzene and toluene. Will that be true for the vapor? So I want you to pause, think about that, come up with an answer, and see if you're right. Okay, so hopefully you thought about this, and with the previous discussion gave you some clues that it is not the same. Because benzene is more volatile than toluene, there'll be more benzene in the vapor phase than there is toluene, because benzene is the more volatile component. And we can take advantage of this fact to separate these two substances from each other. So anyway, we're going to continue looking at different types of diagrams to help us understand the behavior that's going on here in the next videos.